Have you ever stood on the deck of a cruise ship in open water and felt the horizon tilt slightly beneath your feet and wondered why the ship doesn't just keep going? A structure taller than a 20-story building, heavier than 60,000 cars combined, floating on nothing but water, tilted by wind and waves every few seconds, and yet it always comes back upright. That's not luck. That's not a rounding error in engineering. That's a precise physical system working every second you're on board, whether you notice it or not. Today we're breaking down why a 200,000-ton vessel doesn't capsize, even when the sea genuinely tries to make it. Here's the part that doesn't make intuitive sense. If you push down on one side of a floating object, common sense says it should tip. Keep pushing, and eventually it flips. Waves push on a cruise ship constantly, from every angle, at heights that can reach several meters in rough weather. By that logic, a ship this tall and this heavy should be one of the least stable structures on the ocean. It has a huge amount of mass sitting far above the waterline, cabins and pools and theaters stacked a dozen decks high, and yet cruise ships routinely sail through storms that would capsize far smaller boats. The question isn't whether physics allows this, it's what specific mechanism makes it possible. Let's put the scale in context. A large modern cruise ship can weigh over 200,000 gross tons and displace roughly 50,000 to 60,000 tons of actual water. It can stretch beyond 360 meters in length, taller than the Eiffel Tower is high when measured from keel to funnel, with 18 to 20 decks stacked above the waterline. On board, you're looking at 6,000 to 9,000 passengers and around 1,500 to 2,300 crew, all living, walking, and moving weight around the ship simultaneously. The vessel generates enough electrical power to supply a small city, uses hundreds of tons of fuel per day, and produces its own fresh water continuously. Every one of those numbers adds mass, and mass in the wrong place is exactly what should make a ship unstable. So the real engineering question is this: how do you keep something this top-heavy upright, hour after hour, in unpredictable seas? Most people assume a ship floats and stays upright because it's hollow, like an empty bowl resting on water. That explanation is incomplete, and it doesn't explain stability at all. Being hollow explains why the ship displaces enough water to float in the first place. It says nothing about why it doesn't roll over. A hollow shape can still capsize instantly if its weight is distributed the wrong way. The real answer isn't about the ship being empty. It's about where the weight sits relative to where the water pushes back. To understand this, we need 2 points that exist on every floating vessel. The first is the center of gravity, the single point where the ship's entire weight effectively acts, determined by everything on board: the engines, the ballast, the decks, even the passengers walking around. The second is the center of buoyancy, the point where the upward force of displaced water effectively acts, determined by the shape of the hull below the waterline. When the ship is sitting level, these 2 points line up vertically. But the moment a wave tilts the ship, the underwater shape of the hull changes, and the center of buoyancy shifts. The center of gravity stays roughly where it was. That separation between the 2 points is where stability actually comes from. When the ship rolls to one side, the submerged hull shape becomes asymmetric, and the center of buoyancy moves toward the side that's now deeper in the water. This shift creates what's called a righting moment, a rotational force that pushes the ship back toward upright. Naval architects measure this using something called metacentric height, usually written as GM. It's the vertical distance between the center of gravity and a theoretical point called the metacenter, which describes how the center of buoyancy shifts as the ship tilts. A larger GM means a stronger righting moment and a more stable ship. A GM too small, or worse, a negative one, means the ship has no natural tendency to return upright, and that is genuinely dangerous. Every cruise ship is designed and continuously monitored to keep GM within a safe operating range. Here's where it gets more specific to how the ship is actually engineered. The hull is intentionally built wide relative to its height, which increases what's called the waterplane's moment of inertia, a technical way of saying the hull resists tilting more effectively the wider it is at the waterline. Below the visible structure, ballast tanks are positioned low in the hull and filled with seawater specifically to lower the center of gravity, counteracting all the weight stacked in decks above. Heavy machinery, engines, and fuel tanks are also placed as low as possible in the design phase. not as an afterthought, but as a deliberate stability strategy from day one. None of this is decorative. Every one of these choices exists to widen the gap between the center of gravity and the center of buoyancy, because that gap is what generates the righting force every time a wave pushes the ship off level. Static stability from hull shape and ballast is only half of the system. The other half is active. Modern cruise ships use retractable stabilizer fins, essentially large underwater wings mounted on each side of the hull below the waterline. As the ship rolls, sensors detect the motion, and the fins rotate to generate lift in the direction that counteracts the roll, similar in principle to how an aircraft wing generates lift, just applied sideways against water instead of air. These fins don't stop the ship from tilting entirely, and they're not meant to. Their job is to reduce the amplitude and speed of rolling motion, making it far more comfortable for passengers and reducing the mechanical stress on the ship's structure during sustained rough weather. Combined with the ballast system, this creates a layered defense: passive stability from hull geometry and weight distribution, and active correction from stabilizers responding in real time to sea conditions. There's one more factor that can quietly undermine all of this, and it's called the free surface effect. If a large tank on board, whether it's ballast, fuel, or fresh water, is only partially filled, the liquid inside can shift as the ship rolls. That shifting liquid effectively raises the ship's center of gravity and reduces stability at the exact moment stability matters most. This is why ballast and fuel systems on cruise ships are carefully managed, often using multiple smaller compartments instead of one large tank, specifically to limit how much a liquid surface can move and destabilize the vessel. It's a detail passengers never see, but it's treated as seriously as the hull design itself. So what happens when this system is pushed to its actual limit? In real operations, cruise ships avoid the worst of a storm through routing, not brute stability, because avoiding extreme wave conditions is always safer than testing a ship's absolute limits. But when stability calculations do fail, the cause is almost never simply wave height on its own. It's usually a compromised hull letting in water where it shouldn't, or cargo and ballast shifting unexpectedly, both of which move the center of gravity in ways the design never accounted for. The Costa Concordia grounding in 2012 is a documented example. Hull damage allowed uncontrolled flooding into lower compartments, and the resulting free surface effect and shifted weight overwhelmed the ship's righting capability until it listed beyond recovery. That event wasn't a failure of buoyancy or basic stability physics. It was flooding altering the center of gravity faster than the ship's stability margin could compensate. This is exactly why watertight compartmentalization, damage control systems, and continuous stability monitoring exist on board every modern vessel, because the entire safety model assumes something eventually will go wrong, and the ship needs enough reserve stability to absorb it. So it's not the size of a cruise ship that keeps it upright, and it's not luck that gets it through a storm. It's a continuous, engineered relationship between where the weight sits and where the water pushes back, reinforced by ballast placement, hull geometry, active stabilizers, and constant monitoring of a single number most passengers will never hear mentioned: metacentric height. Every roll you feel on a rough night at sea is the ship actively correcting itself over and over, faster than you can consciously notice. But stability is only one layer of how a cruise ship keeps thousands of people safe at sea. What happens when someone goes over the railing in open water with no ship nearby to help? I've broken down that exact protocol in another video,